it's early.
Yeah.
Is the sun up?
No, it's dark,
It's
dark
dark.
outside.
Okay.
It's
Yeah.
winter now.
Yeah.
Oh yeah, winter. Yeah. Sorry.
So we wait for the audience, Prof. So I think about after that, Prabha will introduce you, and then we will start at 3 or 7 at UK.
Okay.
Yeah.
When is the best time for me to share my screen?
So I think
Once I will once I finish reading your bio, and I will invite you in.
And then I share my screen.
yeah.
Okay.
Yeah.
So at the beginning, it just need a few seconds to
No
set.
issues.
Yeah.
No issues.
And what time should I aim to finish my talk before the questions?
But I think the presentation is about 1 hour.
Okay.
Okay. If okay, just 1 hour, and then we have 30 minutes for Q&A session.
Okay.
Yeah.
Yeah.
You say to have the phone near.
Prof, you don't mind me asking, how long have both of you been married?
Good question. 38 years, I think.
38 years. Wow.
Oh.
And your youngest is out of university?
Yeah.
All right.
Yeah, they've all left home.
All flown the nest.
It's good. Yeah, it's quieter now.
It's quite.
Yeah.
So, Prof, are you still working with the Great Britain cycling team?
Yep.
Oh,
Yep.
okay.
We're actually testing today for the next Olympics.
Okay. Great.
I've cut back on admin and teaching, but still fully involved in research. Yeah, it's good.
Yeah.
And again, since you are officially out of the what I call the employment system, can you still go ahead with national grants and all that?
Yeah, I can still be involved because we have an emeritus system.
As a what do you call
It's called an emeritus professor.
Emeritus, yeah.
No,
Yeah,
no. What I mean for the grant as a what primary researcher, chief researcher.
Yeah, it's not possible to be the primary lead if
not possible.
Lead immediately, yeah.
Okay.
Yeah, I think at first I found you because I quite to have a speaker that relate the nature with the science and technology. And then before you, I tried to approach one guy from US. He's a mathematician, Ken Ono, his name, and he used the mathematics to model the swimming team of United States.
Yeah.
Yeah. Yeah, and he got a model that can swim very fast using the mathematics. So that's why I try to do in ISICS. It's not just a research talk, but something that can, give impact to the young generation to love science.
Yeah. Mm-hmm.
Why mechanical, Prof?
Do you mean why did I study mechanical?
Yeah.
I think I enjoyed the mechanical side the most with Lego when I was young. And yeah, but of course the electrical and the other sides are really important. But yeah, mechanical, I just enjoyed that.
Oh. So were you a very build your own things kind of person?
Yeah, I think so.
Okay.
Yeah.
All right.
And engineering is very creative. Some people don't realize
Yeah.
it's very creative.
Do you have a shop at your workshop at your home?
Yeah, yeah,
Oh,
big one.
man. All
Yeah.
right.
With 10 bicycles.
10
Oh.
bicycles.
Okay, I think probably you can
Yeah.
start. Yeah.
Okay.
Yeah.
All right. Okay. Salam sejahtera, selamat pagi, and a very good morning to all gathered here virtually. We are here for International STEM and Innovation Colloquia Series 27, which will be our last series for this year and also the last series before we rebrand for next year as Cosmos of Curiosity. Thank you to Drs. Nazri Halif, our director and producer, and Dr. Sharifa Nur Faiza, as well as UNIMEP Vice Chancellor, Prof. Zaliman Sauli, and Deputy Vice Chancellor, Research and Innovation, Prof. Rizal Fandi, their respective offices, and broadcast control team here, led by Mr. Shahrizan, for hosting this event. I'm Prabha, the moderator for this Series 27 ISICS. Before we begin, as is normal, I would like to introduce our esteemed speaker for this Series 27, Prof. Stuart Burgess. Prof. Stuart Burgess excels in mechanical engineering, both in man-made devices and God's design in nature. His research interests include bio-inspired design, biomechanics, and design in nature. He has worked in the industry as a professional designer, working on projects for the European Space Agency, ESA. He has published over 180 secular papers on the science and design and has been co-editor of the International Journal of Design and Nature. He has lectured at both Cambridge University and Bristol University in the UK. Now he is a visiting professor at Liberty University, USA. From 2004 to 2011, he was head of the Department of Mechanical Engineering at Bristol University. Prof. Burgess was also recognized for his invaluable work in Olympic bicycle design. Since 2014, he has led a team of researchers at Bristol University to develop ultra-high efficiency chain drive technology. His team's advances were used by the British Olympic cycling team at the 2016 Rio Olympics and helped to contribute to Team GB's multiple world records and 6 cycling gold medals. Prof. Burgess has taught engineering design at Cambridge University and Bristol University in the UK. He has won many national awards for engineering design, including the Turner's Gold Medal and a Mullins Design Prize. He has 7 patents and carried out design projects for industry, including designing parts of rockets and spacecraft for the European Space Agency. He is the author of the books Hallmarks of Design, He Made the Stars Also, and Design and the Origin of Man. He has lectured in many countries, including the USA, Australia, Singapore, and Japan, and today in Malaysia. On a personal note, he is married to Jocelyn for 38 years and they have 5 children. We wish you a very good morning, Prof. Burgess. If anyone wishes to ask anything, hope you do not interrupt Prof. Burgess during his talk. It would be better if you could type it at the chat box. We will read it at the end. Questions you can ask also at the end. Thank you. Prof, the floor is yours.
Yeah, thank you very much for your introduction. It's good to be with you. At the beginning, I just need to share my screen. Has that come up?
Yes. It's not
Okay.
full screen.
Yeah, so that is a... Okay, has that come up to the full screen?
Yeah.
No. Okay, that's good. So yeah, it's good to be with you. I'd just like to say at the beginning that the work in my presentation has been supported by Bristol University in the UK, Cambridge University in the UK, and also the Discovery Institute from the United States. So I'm going to be talking about using engineering to reveal nature's secrets and give examples of that. At the beginning, I just want to make a plug for science, technology, engineering, and maths. When I first studied mechanical engineering, I hadn't really appreciated how important engineering is to solving so many of the world's problems with energy, food, the environment, and medicine. So it was very encouraging when I graduated. I realized how important engineering is today, but also fun as well. I had the privilege of working for the European Space Agency, and I worked very much on Envisat, the largest Earth observation satellite in the world, which has played an important role in monitoring the environment. That was really great fun. Also great fun, as you've heard, I helped the British Olympic cycling team over the last 3 Olympics, and that's been really great fun. A lot of people don't realise how important the equipment is in sports like cycling and pole vaulting and rowing. I think sometimes the engineers deserve some of the medals, not just the athletes themselves. So that's great fun. And also working on medical equipment. I've really enjoyed working on prosthetics and robotics and rehabilitation. Medical, the area of medicine is very important now, and engineers are making a very important contribution in the area of medicine. So there are lots of opportunities in science, technology, and engineering. I really recommend it to students and young people. Also, just a quick plug about Asia. In Asia, many companies are becoming leaders in electronics and artificial intelligence and robotics, including Malaysia. It has a reputation as an emerging semiconductor powerhouse. So if you're an engineering or science student in Asia, you have many opportunities to make a big impact on the world. So I just wanted to make those two plugs at the beginning. But as for my presentation, I've got 3 objectives. One is to show how engineering insight can be really essential to understanding biology, and that has a double benefit. Firstly, it helps biologists to understand how organisms work, but also it gives an opportunity for bio-inspired design for engineers to make better products. So it's a double benefit. Also, I want to briefly argue that biology students can benefit from learning engineering principles. Of course, biology is already a huge, challenging subject, but there's definitely a great benefit in biologists understanding engineering principles, and then to show how bioengineering is growing in importance today. So those are the objectives. So to make this point, engineering insight can be essential to understanding biology. So we have this traditional view that biology is mostly chemistry. So to understand biology, obviously you do have to study the fundamental principles of chemistry, chemical reactions like diffusion, bonding, ion channels, and so on. But there's a modern view now. If you look at the composition of research teams and modern research, you're seeing that biology is really chemistry plus engineering. By engineering, I mean studying material properties like density and strength and stiffness, understanding principles of levers and linkage systems, tribology, different types of joints and structures, types of flights, the laws of thermodynamics, systems engineering, feedback control, multi-objective optimization, and trade-offs. And so now researchers are understanding that rather than just seeing organisms as chemical reactions, you've really got to stand back and looking at the engineering, organization, and design of organisms. And so that's becoming the modern view, and I want to bring that out in this talk. There have been quite a few important books on engineering in Nature, and I'll just mention a few at this point in case you want to make any notes. There was a really important book over 100 years ago by Darcy Thompson on growth and form. This was one of the first really detailed books showing how mathematics and physics are important for really understanding and modeling organisms. So that was a very famous book, and it's still really relevant for today. A huge book, but very, very good. Since then, there have been lots of books. Steve Wainwright and Julian Vincent, they're both from the UK and produced really important books focusing on the mechanical design of organisms. Then we come to Adrian Bejan and Stephen Vogel. They're both from the United States, actually both from Duke University. These two authors have produced very good books explaining the engineering side of natural organisms and in nature. Stephen Vogel has produced a really comprehensive book, Comparative Biomechanics. Definitely recommend that. And later I will explain that I'm going to be producing a book coming out in February next year, just a few weeks now, called Ultimate Engineering, describing how we see ultimate levels of engineering in biological systems. So I'll mention a little bit about that later. So there are some books on engineering in nature. So what I'm going to do now is go through some case studies, which hopefully will be interesting. The first four will be on human biomechanics, looking at various joints in the human body, and then some examples on animal biomechanics, looking at fish, birds, and then the vertebrate limb pattern. So first of all then, we go through the human biomechanics examples. So first of all, we start with the knee joint. Now, the knee joint is a really nice example to show the importance of understanding engineering to understand biology. What's interesting about the knee joint is it's a very strong joint. It has to be, because if you do an activity like jumping, the load through the knee can be up to 8 times the body weight. So that's an enormous force that can go through the knee joint. But on the other hand, the knee joint has a very large range of motion. In the middle, you can see this lady is flexing her knee. That looks like about 160-degree angle of flexion. Women are slightly more flexible than men, but both men and women have this large range of motion in the knee joint. Now, for an engineer, this looks really unusual and impressive, because if you have a very strong joint, it normally is very difficult to have a large range of motion. For example, if you look at the femur and the tibia bone, what you notice is that they have a large radius. They need a large radius at their interface, because if it's a very high loaded joint, then you need a large radius to reduce the stresses. But when you look at the femur and the tibia, you have to think to yourself, well, how can you get 160-degree flexion? Because it doesn't look as though that femur could rotate. If it's a normal joint with a fixed point of rotation, like the joints in the fingers or the elbows, you couldn't possibly get that rotation. Well, engineering explains how this is possible in the knee joint. So what happens is this: in your knee joint, the femur in the upper leg and the tibia in the lower leg, they roll around each other. So what this diagram is showing is the femur flexing and rolling around the tibia. If you look at the right-hand diagram, you can see the center of rotation is moving. So the knee joint is an unusual joint. It doesn't have a fixed center of rotation. It's actually a type of floating joint. So the femur floats around the tibia. In an adult, the center of rotation can move by around 2 centimeters, which is actually quite a big movement. And because of this rolling motion, the femur is then able to flex through a large range of motion. So how does this rolling take place? Well, it takes place due to a linkage mechanism. Now, when I talk about a 4-bar linkage mechanism, an analogy would be in a motor car, the steering system or the suspension system, they're linkage systems. This one is slightly different to that in that it's an inverted 4-bar mechanism. So you can see the 4-bar linkage system with the 4 dots and the 4 bars. The solid bars represent the cruciate ligaments in the knee. The cruciate ligaments are those 2 crossed ligaments in the middle of the knee. One is the posterior cruciate ligament, labeled PCL in the diagram. The other is the ACL, the anterior cruciate ligament, labeled on the right-hand diagram. And they are these cross ligaments in the middle. But together with the bones, they effectively form a 4-bar linkage. Now, in mechanical engineering, it's well known that if you have a linkage mechanism, you can fine-tune motion and forces. In this case, you're fine-tuning this rolling motion and a moving center of rotation. So this is a very clever system for creating a joint that can do 2 things that normally you cannot do together. It's both a strong joint with a large radii for transmitting large loads, but at the same time, it has a large range of motion. If you look at many biology books, particularly traditional biology books, it says, well, this is a complex hinge. Not many biology books actually explain the mechanics and the 4-bar linkage system that enables this large range of motion. So this is an example of how engineering explains biology. In my lab, I've also produced bio-inspired joints based on the system. So it's a double benefit. It shows biologists how the joint works, but it helps engineers to produce better joints for prosthetics and also for robotics. So this is now giving you just a little animation of how the femur rolls against the tibia. So the 2 brown links are the cruciate ligaments, the anterior and the posterior, and the blue bars are effectively produced by the bones. So now you can see why if you have an injury and you snap, say, your ACL, that's often the one that goes first, the anterior cruciate ligament, you can see why your knee then becomes unstable, and normally it's important to have surgery to put that cruciate ligament back together. One more aspect of the knee joint. Here's a quotation from a journal paper where the author from Imperial College in London, he said, "It is remarkable that knees undergo millions of cycles of loading with no wear." Engineers are really astounded at the tribology of joints. The friction levels in joints is incredibly low and the wear rates are incredibly low. On my work for the British Olympic cycling team, we got friction levels in our chain down to extremely low levels, something like a coefficient of friction around 0.1, and we thought that was as low as you could go. But in human joints, the coefficient of friction can go down to something like 0.002, 1/50th of what we achieved in the Olympics. When we first saw that, we could not believe that. And this has astonished medical researchers and engineers. Just to give you a glimpse of how that happens, the cartilage in our joints releases synovial fluid, and the more you load your joint, the more fluid is released, and it creates like a thin film lubrication, but also the synovial fluid. It circulates nutrients and it distributes load and even acts as a shock absorber. What is interesting, and there's a lot of research still going on at this moment, there are different lubrication techniques. There are at least 3: boundary lubrication, hydration lubrication, and fluid film lubrication. Normally with engineering systems, you normally have one type of lubrication technique, but in joints, in animal joints, at different scales, you have different effects happening. It's very, very complicated. And I'll just show you one slide which summarizes these 3 types of lubrication. I would love to be able to copy this for the next Olympics. It would probably guarantee medals, but it is so complicated. It's extremely hard to copy this, but a lot of effort is going into trying to produce bio-inspired types of synovial lubrication. So for the boundary lubrication in animal joints, the joints are constantly producing a lubricin protein, a macro molecule, and lubricin protein is a very clever molecule. It has an affinity for cartilage, and it self-assembles not only to the cartilage but with other lubricin proteins, and it forms a single molecular layer, and on both layers, on both sides of the cartilage, and you get a slip plane in between, an ultra low friction slip plane. But not only that, you have this hydration lubrication with phospholipids, similar to in the membrane of cells, and they also form a molecular layer on the cartilage, and again you get this ultra low friction slip plane. But on top of that, you get thin film lubrication. When you load a joint, in an animal joint, when it's loaded, the cartilage compresses because it's elastic and it's a porous material. And when it's compressed, interstitial fluid, the synovial fluid, is released and it forms a thin film lubrication through hydrostatic pressurization. And that, for very high loads at low speeds, that separates the surfaces. And this is the most impressive thing. When you have a low speed, high load bearing, it's very hard to create a thin film. Engineers can create a thin film fairly straightforwardly at high speeds, but at low speeds it's very difficult. And a lot of effort is going into seeing how we could copy what happens in these natural joints. Engineers are developing hydrogels. There's a lot of research, a lot of publications going on at the moment which copies some of these principles. So this is quite an exciting area of research at the moment. One other thing on the knee joint. On the right is a robotic knee joint that my lab produced. This is one of the papers in the Journal of Mechanics and Robotics, the American Society of Mechanical Engineers. So we produced this for a robot. We put this 4-bar mechanism on the side of the joint. It was easier than putting it in the middle, as happens with animals, particularly humans. So you can see our 2 cruciate ligaments. Now on the right hand side, if you look at the more horizontal of the ligaments, you can notice we have a compression member in there. Now this was fascinating because as we were testing our robotic knee joint, we noticed that it became unstable unless we put in a compression member. And then looking at the literature, we realized that the human knee joint can also become unstable if you don't have enough strength in your muscles and ligaments. And what we realized is that when we were testing our robotic knee, we could model how the human knee becomes unstable if it doesn't have the right support around the knee joint. And so we looked at some of the conditions for instability and we published that in the American Society of Mechanical Engineers. So again, this was giving insight to biologists, but also helping us to produce bio-inspired designs. Here you see this dual benefit of applying engineering principles to biology. But now I want to look at the next case study, which is the foot-ankle complex. Like the knee joint, the foot has to take high loads. In fact, the foot takes the biggest loads of the whole body because it's right at the bottom. So if you're jumping, then you can have 8 times the body weight going through one foot. So it's extremely highly loaded, and the foot is multifunctioning as well. It has to have a structure for standing on one leg, on the toes. It has to be a stiff lever for push off, but it also has to have the ability to be flexible for landing or for various activities. Now that's a really difficult combination because normally you would design something either to be stiff or to be flexible, but the foot has to do both. So it has to transition between stiff and flexible. That's a really hard thing to do. And then of course it has to load function. So let's look at some of those things. Well, first of all, the foot needs 3-point contact for standing. You've probably heard how it's better to have a 3-legged stool than a 4-legged stool because a 3-legged stool gives you the perfect 3-point contact with the ground. Well, the same is true of the foot. It's relatively easy to stand on 2 legs, you can see on the left, because you put your center of gravity through a trapezium on the ground. But humans have a unique ability for mammals to stand on one leg. So the lady there is standing on one leg. When she does that, she is putting her center of gravity through 3 points. You can see on the top right diagram. The foot has a 3-point contact. So she puts her center of gravity, that symbol, between those 3 points. Humans can also stand on their toes, which is really important for activities like sport and running. For example, apes cannot stand on their toes and they find it extremely hard or impossible to stand on one leg because they do not have these 3 points of contact. But we can make 3-point contact even for standing on our toes because we have a strong big toe that points forwards, and then we can put our center of gravity through those 3 points. This is something that is often not explained well in biology books because it's a mechanical principle. Again, an example where engineering is needed to explain the functionality of the foot. But you have this question, how can the foot generate those 3 points of contact? Because you do not see this at all in apes or other animals. Well, the answer is the foot has 3 arches that form a triangle. And not only are there 3 arches, but they even give you the maximum spacing, because the maximum triangle you can make, the easier it is to stand on one foot and to stand on your toes. So we have 3 arches. One is the medial arch through the 3 biggest toes, and you can see which part of the triangle that gives at the bottom. Then we have a lateral arch through the 2 smallest toes. So both of these arches have a point on the heel, but the medial arch has a point at the base of the big toe, and the lateral arch has a landing point at the base of the little toe. And then there's a transverse arch which integrates the medial arch and the lateral arch. Now, all 3 of these arches are like Roman block arches, and each one of them even has a keystone. You've probably seen a Roman arch with blocks, wedge-shaped blocks, and you've probably seen the keystone at the top. Well, each of these arches has a keystone at the top and like a Roman block arch, except it's more complicated than a Roman block arch because each of the bone segments are linked by ligaments and can become flexible. In one direction they're flexible, but in the other direction they're stiff, like a Roman arch. So here is a picture of the foot in the push-off position. So when you're running or walking, you push off your toes as shown. Now, when you're running and you push off, you need a stiff lever. So your foot needs to become very stiff, like that Roman block arch. But when you land on your foot, or when you're doing an activity like tennis, you need your foot to be flexible. Then you need your foot not to be this Roman stiff arch, but a flexible arch where the ligaments stretch. So how does the foot reconfigure from flexible to stiff and stiff to flexible? Remarkably, we don't think about this, it just happens automatically, but the foot has a remarkable ability to transition between stiff and flexible. This is the reason why engineers have not been able to produce a functional prosthetic foot. You can get a prosthetic knee joint and a prosthetic hip joint with more or less the same functions, never as good, it's the real thing, but emulating some of the functions of a knee and a hip joint. But when it comes to the foot, there are basically no prosthetic feet that have the functions of the human foot. And the reason is it is so difficult to simulate this reconfiguring ability from flexible to stiff. So how does the foot do it? Well, once again, engineering explains how this happens. First of all, at the bottom of your foot, you have this huge ligament called a plantar fascia, very thick ligament. Next time you have your shoes off, you can actually feel this really thick ligament at the bottom. Now, normally it's not rigid and stiff, but when you go to push off, in fact, if you could do a little experiment, and if you push off your foot and bend down, you can feel it stiffens up automatically. So when you push off your foot, the plantar fascia automatically stiffens up and it creates this stiff Roman arch, and your foot becomes remarkably stiff. Secondly, that transverse arch that goes across your foot also stiffens up the medial arch. The transverse arch is slightly curved, and in the same way that a piece of paper or card, even though it's very flexible when it's flat, if you put a curve in a card or a piece of paper, it suddenly becomes a little bit stiff. And the same is true of the transverse arch. That also stiffens up the medial arch. There have been recent papers explaining that. Also, when you push off, your muscles tighten. Your big toe is very, very stiff compared to, for example, apes. Also, the alignment of the bones. If you look at the three big toes in red, if you follow the bones back, you notice that when it gets to the ankle, the talus, it's all in alignment, whereas the lateral arch, the two smallest bones, the force doesn't go into that final bone. So your foot is so designed that all the force of your leg through the tibia is all aligned to go through the three biggest toes. And so when you land, a natural running motion is that you land on the outside of your foot, you land on the two small toes on the outside of the foot, and the load doesn't go right up through the leg because of the alignment of those two toes. So when you land on your foot, the plantar fascia becomes looser, the muscles become looser, you land on the two smallest toes, and your foot becomes flexible. And this all happens without really thinking about it, because on the bottom of your foot, you have the order of 7,000 sensors. It's one of the most highly packed areas for sensors, and the brain is monitoring what is going on with the foot, its position, whether it's pushing off, whether it's landing, and so the foot reconfigures. So the foot has these incredible arches. By the way, this makes the human foot extremely different to the foot of an ape. It's one of the parts of our bodies which is really very, very different. Recently, I've been publishing on the foot. In 2022, I published in Biocomplexity why the ankle foot complex is a masterpiece of engineering. I also rebutted the claim of bad design. Some people have claimed there's bad design in the foot, but I kind of answered that. And in 2023, I published in the Journal of Biomimetics a paper on a new prosthetic foot, where I was actually copying the functionality of the foot, the arch of the foot, a prosthetic foot where you could stand on the toes. So this is meant to be a contribution to creating a foot prosthetic that can copy the functionality of the human foot. There are many more steps that need to be taken, but research is going on, making progress, but it's hard because of the complexity of the foot. So that was produced in my lab just a couple of years ago at Bristol University. So once again, engineering helps you to understand biology, but also to then produce some bio-inspired designs. Then we come to the wrist joint. This is very much an unsung hero of the human body. We tend to forget about our wrist joint. It's so small. It's if you're an adult, it's about the size of a golf ball, hidden between your fingers and your lower arm. You tend to forget about it, but it is an incredible design, a lot of research going on at the moment. Like the foot, it is a multifunctioning joint. The wrist flexes, for example, when you're playing the piano, your wrist abducts, adducts, very important for sports like table tennis, which I know is popular in Asia. Your wrist joint forms a carpal tunnel. That's a tunnel for protecting blood supply, nerves, and tendons, because your fingers are driven by tendons, some of which come from your lower arm, so they have to go through the wrist, and the carpal tunnel forms a protective tunnel for that. And also load transfer. If you're doing press-ups, all the weight of your upper body is going through your wrist. So as well as being a delicate joint, complex joint, it also has to be very, very strong. And so your wrist is made of 8 bones. You can see those on the left. There are 2 rows of 4 bones. 4 bones above the lower arm, 4 bones below the fingers. And I'll explain how engineering insight helps to understand the functionality of the wrist. So first of all, the wrist can flex and extend. If you're a good pianist and with a lot of musical instruments, you need to be able to flex the joint with precision. Now, to get a high range of motion, you have 2 joints in your wrist, because I mentioned there are 2 rows of 8 bones in the wrist, 4 in the upper row and 4 in the lower row. That gives you 2 joints, the mid-carpal joint in the middle of the wrist and the radiocarpal joint between the wrist and the lower arm. Now, so that helps the wrist have a high range of motion. The wrist is remarkable in how much it can flex and extend, and it's to do with these 2 joints. But a challenge of having 2 joints is if they do not have the same center of rotation, your wrist would be very floppy. But when you move your wrist, it looks as though you've only got one joint because you have a common center of rotation. But to have that same center of rotation, the two joints need a different radius. Because if you look at the diagram on the right, in order to have the same center of rotation, you need the right ratio of radius to the midcarpal joint to the radiocarpal joint. The radius to the radiocarpal joint has to be much larger than the radius to the midcarpal joint, and just the right ratio that gives you a common center of rotation. And research has shown that you do approximately get the same common center of rotation. That helps the precision of movement of the hand. Remarkably, exactly the same happens in adduction and abduction. So when you're moving your wrist side to side, and it's a remarkable range of motion, one of the reasons you have a good range of rotation is that you have two joints, again, midcarpal joint and radiocarpal joint. And again, it moves smoothly and predictably because, again, you have a common center of rotation, because the radius of those two joints is approximately the right ratio to give that common center of rotation. So you see fine tuning of design in the wrist joint. Again, engineering gives you that possibility of having that insight to see how that happens. Then you have another question: how does the wrist joint perform 4 different functions? This flexion and abduction, load transfer, carpal tunnel. The answer is the 8 bones have a unique arrangement. It's hard to think of any other arrangement of 8 bones that gives these 4 functions. If you look on we've already seen the flexion function and the abduction function. If you look on the left of the diagram, you can see 2 load columns for the load transfer function. Now, engineers know that if you have 5 fingers, but you have 2 bones in the lower arm, it's very difficult to get a smooth load transfer, because 5 and 2 are 2 very different numbers. How do you get 5 load paths into 2 load paths in the radius and the ulna in the lower arm? Well, the 8 bones of the wrist are just so arranged that you get basically 2 columns through the 5 fingers, and they go into the 2 columns of the lower arm. And you can see this through the shading there. So the 8 bones are just right for producing effectively 2 load columns, even though there are 5 fingers. But on the right hand side, you can see how a carpal tunnel is formed through 6 bones of the wrist. All 4 at the top row are formed, you can see them in dark blue, but also 2 of the lower bones also form that carpal tunnel. So with the wrist, not only do you have the bones that are just right for the flexion function and the abduction function, but they're just in the right place to give you these other arrangements. The carpal tunnel is remarkable because it's giving you an arch in the perpendicular direction to the other arches. So you have this, it's like a 3-dimensional puzzle working in different directions. So in 2024, last year, I published a paper in Biomimetics. It was chosen as the cover paper on the journal, as you can see. And actually, I hadn't really appreciated this, just looking at it now. On the cover of the journal, you can actually see the 4 functions. And so what I explain, if you look at the bottom row of my table, I show how 8 bones perform 4 different functions. It's like the hardest 8-piece puzzle you could challenge yourself with, but it's just the perfect design for giving those 4 functions. And in that paper, I argue that in order to produce better robots, engineers, one of the things they're lagging behind, if you compare engineering with biology, what you find is biological systems have a much better use of multifunctioning. There are huge advantages in multifunctioning. You can produce a much more compact design. If you look at prosthetic wrists, you find they're very, very bulky because they're not multifunctioning. In fact, reviews have taken place explaining that prosthetic wrists are just far too bulky. And in the paper, I explained that engineers need to copy this multifunctionality if they're to create compactness. If you don't have a compact joint, it becomes heavy and you have this knock-on effect. You need more electronics, you need more power. To produce compact robotics, we need this multifunctionality. So at number 4, I talk about the fingers, just to give you a kind of a fun fact. I don't know if you know this, but there's a kind of Olympics for knitting. And in the Olympics for knitting, the challenge is how many stitches can you make in 60 seconds? And if you take into account, there are about 8 steps with the fingers to make one stitch. I think I can make one stitch in 60 seconds. But the world record is 118 stitches in 60 seconds. That's almost 1,000 movements in 60 seconds. If you look in the Guinness World Records, I think Miriam Tagles is the current world record holder. The dexterity involved in knitting is just incredible. If you ask an engineer, build a robot that could do stitches, it would just be impossible to match the human dexterity. So here are some of the unique features of the human hand. Humans have this unique opposable thumb, not only opposable with each finger, but even a tripod grip to hold a pen, as you can see bottom left. We also have remarkable arches in the hand, longitudinal arch, distal arch, proximal, transverse arch. And our hand has this perfect design for holding round objects. Even our middle finger locks in order to have a strong grip. So these are some of the unique features of the human hand. I explained how the human foot is remarkably unique, and so are our hands and our feet. From a mechanical point of view, the pinnacle of mechanical design of anything we know, but 2 things that make humans unique. So here's a question that engineering can answer. How can a finger have 7 muscle tendon units? Because that dexterity that knitting champion had, and the dexterity that all of us have when you tie shoelaces, when you cook and drive, you have amazing dexterity in your fingers. We tend to take that for granted. But if you could look under the skin of your finger, you would be astonished at the intricacy, the detail of design, because you have 7 muscle tendon units in your fingers. Your fingers are incredibly slender. One of the reasons is we don't have muscles in our fingers, we have tendons, and those tendons are driven by remote muscles, either in our hand or our lower arm. That keeps our fingers slender, but we still have 7 muscle tendon units, for example, in the index finger. You have 2 tendons on the bottom of your finger, reaching different parts of your finger. You have effectively 2 tendons on the top. It's more complicated. And you also have around 3 tendons around your knuckle joint to give you this kind of angled force. And you have all of these guide tunnels, especially on the palm side of your fingers, because as you tug, it's like a cable system, like the brake system on your bicycle. When you tug the cable, you need these guide tunnels to stop the cable pulling away, but also the guide tunnels also have this synovial fluid, a sheath, to have precision smooth motion. What you're looking at on this diagram is so complex, engineers cannot copy this. I've produced exoskeletons in my lab, and we cannot copy this. We can produce maybe 3 or 4 tendons for simple motion, but we cannot produce this level of complexity. To give you an example of how the fingers work, when you flex your finger to form a fist, as you see on the left, what you're doing is your brain pulls the long flexor tendon that reaches the end of your finger on the palm side of your hand. Your brain has the ability to tug those 7 tendons exactly in the right combination. And of course you do it without thinking about it. So when you flex your fingers, your brain pulls that long flexor tendon. When you want to straighten your fingers, as you see on the right, your brain then pulls the long extensor tendon on top of your fingers. So your brain obviously knows what's the long flexor tendon and the long extensor tendon. If I just go back, if you look at the top, you notice one of the tendons goes to the last part of the finger and one of the tendons goes to the second last part. So you have a long tendon and a shorter tendon. So when you pull your long tendons, you can flex and extend your fingers. But you can also do a half finger flexion. Some people are better than others at doing this. I mean, some people can even flex the very last part of their finger. I've seen people do that. So if you want to flex just half of your finger, then you're pulling the short flexor tendon, and then you're pulling the short extensor tendon. So this explains why you have 2 tendons on the top and 2 tendons on the bottom, because you can flex in different ways. And of course, your brain knows which is the short and the long flexor and extensor. But then your brain can make your finger do more complicated things. For example, you can do a straight finger flexion and you can do a straight finger extension. So you can flex your fingers at the knuckle while keeping a straight finger. This is more complicated. In this case, you're pulling a tendon that goes across your knuckle. It's the lumbrical tendon, and it's very cleverly positioned just in front of the knuckle. On the left, you can see that you can flex your finger even though it's kept straight, because you use your extension flexor to keep it straight at the same time as pulling the lumbrical to flex the knuckle joint. So that's a clever thing, but the brain has to now be tugging different tendons with just the right ratio of force. Then to go back, the brain says, okay, now I will pull the long flexor with a greater force than the lumbrical to pull my straight finger back. Now things start to get super complicated when you do this particular motion, which is quite an incredible motion. When you pull your index finger, you know, if you're tapping a key on your mobile phone or you're tapping a piano note, you do this very special motion, push and pull with your finger. Now, this is a super complicated motion because some of the joints in your finger you are flexing at the same time as extending other joints. Now, when you first look at this, you think, well, surely this is impossible because my long tendon, my long extensor tendon can only extend, my long flexor tendon can only flex. So how can I possibly combine flexion extension in one movement? Well, in this case, the brain is doing super clever things and it's tugging on different tendons in order to get this special motion. For example, on the left, the brain is tugging the lumbrical tendon, which will, at the same time as flexing the knuckle joint, extends the next 2 joints in the finger. So the lumbrical joint can both flex and extend joints at the same time. But if you look at the right-hand diagram, I mean, this gets even more complicated. The brain is now pulling on both the short extensor tendon, the long flexion tendon, and the lumbrical with just the right combination to get that motion back up again. So these are very complex motion. And it's interesting, when a child is developing, a baby that's a few weeks old has this instinct, this reflex to do a power grip. But it takes a child a very long time, maybe 2, 3, even 4 years to learn this motion. The brain has to learn this very complex motion of doing this push-pull motion. But then, of course, the fingers also have the interossi to produce the abduction, adduction motion. And one of the most complex motions is the circumduction. And to us, it seems so easy, but it's actually very complicated, because in order to get a constant speed of circumduction, you have to apply a kind of a sine wave of instructions to your abduction muscles and your flexion muscles, because if you don't apply a sine wave, you won't get constant velocity circular motion. So constant velocity circular motion, it seems easy to us, but it's actually very complicated, because you're going through a quadrant of motion. But again, the brain learns groups of muscles and groups of motions to do this. So we take our fingers for granted, but to me, it's the pinnacle of mechanical design. So again, engineering giving insight to how it works, but also inspiration for robot designers. This is one paper I've produced in my lab. We developed an exoskeleton for rehabilitation for stroke patients. Very fulfilling to see a stroke patient actually use this to strengthen their hand to be able to pick up objects. We studied the human hand to know where to put joints. You can see on the top of the right-hand page, we monitored how the human hand could hold a round object, and we copied that in our exoskeleton. So yeah, studying the human hand was a great inspiration for producing this exoskeleton. So a little bit more brief with these examples, but I'll just briefly go through some animal joints. So first of all, fish jaws. This is really interesting because this parrotfish needs a very strong jaw to bite hard coral rocks. But there's a space constraint, because fish have this fusiform shape to have low hydrodynamic drag. And when you look at the shape of the fish, it doesn't have much room in the mouth. And so you have this big problem from an engineering point of view. How do you make a strong mouth, but you've got no room to put muscles in there? And once again, engineering gives you the answer. What you find in many fish are these 4-bar linkage mechanisms, again, like the steering system in a car. And there are two clever things in this steering, this 4-bar system. One is you can put the muscle behind the mouth, whereas in a mammal like a human, we have our mastication muscle, our mouth muscle, basically in by our jaw. In the case of a fish, the muscle is behind the jaw, where there's lots of space to put it. You can have a big, powerful muscle behind the jaw. And you can do that because the 4-bar mechanism reverses where the actuator needs to be. But the 4-bar mechanism also gives you the chance to put mechanical advantage, so you get force amplification as well. So it's a very clever and effective system. And as a result, parrotfish have a remarkably powerful mouth in a compact design. This is what you find in animal joints, a compact design, but highly functional, highly efficient, and highly strong. And other fish have some incredibly complex mechanism. The sling jaw wrasse, you get a lot of these in Asia. I had a Chinese student who came from China to do a PhD with me, and she produced this simulation of the sling jaw wrasse. She had it in her PhD, and we couldn't get hold of a sling jaw wrasse, but she managed to bring one back from China, so in her suitcase. I was very pleased about that. And so this is another interesting linkage mechanism, in this case for linear motion. In 2021, I produced a review of linkage mechanisms in animal joints and related bio-inspired designs. In the last 4 years, that's had 45 citations, and it had 10 particular case studies of different linkage mechanisms in animal joints, showing how the linkage mechanisms gave a very compact design. And even in one case study, there was a latch mechanism, an over-center mechanisms. If you're interested in 4 biomechanisms, do look up that review in the Journal of Bioinspiration and Biomimetics. And here's an example from Malaysia. In this university, they produce some bio-inspired 4-bar mechanisms to give better functionality in a robot hand. So that's an example from Malaysia. It's not, this was from 2020, so a few years ago. So again, some more brief examples. Flight aerodynamics. Biologists have wondered for quite a long time, do birds use aerodynamic braking to make flight more efficient? So the background to this is the following. When birds are flying, they flap their wings up and they flap their wings down. Now, when they're flapping down, they use a lot of energy to create lift. But when they lift their wings up, they're just getting ready for the next cycle. So there is this question, do birds use energy to lift their wings up, muscular energy, or do they simply let the aerodynamic drag let the wings go up? And so biologists have not known whether they just let their wings go up or whether they force them up, and it affects how efficient flight is. So I spent one summer in America in a biology department at Liberty University, and I developed equations of flight, and I showed that the aerodynamic drag, this is one of the equations for aerodynamic drag, I showed the aerodynamic drag on bird wings was enough by itself to decelerate the wing because the mass and inertia of bird wings are so low. We had several gulls and we did measurements. The inertia is so low and the aerodynamic drag is high enough for the bird to use aerodynamic braking, and so the bird does not need to use energy to lift the wings, and that was published in the International Journal of Micro-Air Vehicles. So this enabled the biologists to answer that question. Could they use aerodynamic braking? I've had a project to develop a micro-air vehicle. You can see a picture of our micro-air vehicle there, and that was inspired by the European darter dragonfly. And the reason we could do that is because engineers have studied the flight of insects like bees, wasps, and dragonflies, and they have explained how these insects, unlike birds, they really twist their wings significantly every flap cycle, and it's that twisting that produces these circular vortices. You can see these circular vortices, and they're called leading edge vortices. They come around the insect and they create a kind of a donut shape, and they create what's called a downwash, and it produces very high lift forces, which is possible on a small scale. So engineers have explained how it is that insects like bees can fly with such high lift. And also the second benefit, engineers can produce bio-inspired designs. Sorry, there. And here are some publications on that I've produced in my lab for insect flight and bird flight. Finally, this is a picture of the vertebrate limb. And you can see on the left, the human arm, a whale flipper, a bird wing, a human leg, a feline leg, and a frog leg. Now, this is very much of interest at the moment in robotics, because engineers want to know how optimal is this design. And the reason this is important is because Charles Darwin famously assumed that the vertebrate limb was not universally optimal. And he said, in particular, he said the whale flipper he assumed was a bad design, because he said surely the whale doesn't need fingers, it doesn't need a wrist, doesn't need those finger muscles. And that actually inspired him to produce his theory of evolution, because he said, because he assumed the whale flipper and other vertebrate limbs were not optimal, you could only explain them through the theory of evolution. Now, last year I produced this review paper where I challenged Darwin's assumption, and in fact in my very title I said universal optimal design in the vertebrate limb pattern. Basically I was saying Darwin was wrong in his assumption. The whale flipper and the other animals, the vertebrate limb pattern is actually fully optimal. For example, the whale does need fingers and it does need a wrist. To give you an example, I'll just give you one example, and that's the whale flipper. I showed that the whale flipper does need to be able to morph its shape and stiffness. It's not a stiff paddle as Darwin assumed. It's a morphing structure. It uses its fingers and its wrist to change its shape and to change its stiffness. When a whale is swimming, we now know that because of the hydrodynamics of swimming, the whale does need to fine-tune its stiffness and shape. For example, when it brakes or accelerates, if it can't change the stiffness of its flipper will bend and the drag will go right up, and whales need to swim efficiently. So they have flippers that are morphing structures that can fine-tune stiffness and shape in order to reduce drag. Of course, Darwin didn't realize the hydrodynamics of flight. He didn't realize the aerodynamics of bird flight. And so in my paper, I explained, not just for the whale, but for all animals, the vertebrate limb pattern is actually optimal. And in the conclusion, I said that the great versatility of the vertebrate limb pattern challenges the limb homology argument. And this is one of the reasons why more academics, both biologists and engineers, are questioning Darwin's theory of evolution, saying, you know, some of the fundamental icons of evolution, like the vertebrate limb, are turning out to be actually not correct. And so I think this needs to be mentioned in teaching in schools and universities around the world. So today we have an exciting field of bio-inspired design. These are some examples of recent bio-inspired design. Some wind turbines are being built with serrated edges because that can make the wind turbines more efficient, better lift-drag ratios. Also, vehicles can be very loud, but engineers are looking at the design of owl wings, in particular their serrated edges and other features that can reduce noise. Various animals are being looked at for producing photonic crystals, and then of course prosthetics is a very important area as well. So some brief conclusions. Engineering insight can sometimes be essential to understanding biology, and biomechanics especially benefits from that knowledge. And biology students really would benefit from learning engineering. So we have this modern view. Biology is not just chemistry. Biology is chemistry and it's engineering. You have to look at biological systems as engineering systems. The kind of thing I would recommend biologists to learn, in particular these kind of areas: mechanics, tribology, structures, flight, feedback control, multi-objective optimization. These are the things I would recommend for biologists to learn. And just to mention, if you're interested, my book Ultimate Engineering is coming out on February the 12th, 2026, not long. Now the publisher is the Discovery Institute in the United States, and it argues that biology is much more sophisticated than man-made technology. It argues that we really need to understand engineering to understand biological systems. And it also argues for intelligent design. It argues against Darwin's theory of evolution. Not only is the vertebrate limb showing evidence against evolution, but lots of other areas as well. And in the book, I explain how many senior biologists and engineers are now advocating for intelligent design. So do look out for that. And you're welcome to look at my website for more information on things that I've talking about today. But I absolutely recommend STEM as a very rewarding, fulfilling career. Thank you for your attention.
Thank you, Prof. Burgess, for that complete re-engineering of what I had in mind. That blew my perspectives of mechanical engineering. And also reminds me of what Prof. Emeritus Prof. Carver-Mead does from Caltech. Something similar to what you do, but his is on the microelectronics. He copies, studies human eye, human hearing, bioengineering of those kind of stuff. So quite a lot of that. And I'd like to pose this just as on a jovial manner. How good is James Cameron?
Mm-hmm.
How good is James Cameron with Avatar and all those stuff? Are those real? Are those does he consult you?
Yeah, just a little bit.
Oh, it does. Okay, that's nice. All right. Let me move on to questions. Prof, really thanks for that wonderful re-engineering. Our producer asks, what skills should students develop if they aim to work in bioengineering in future?
Yeah, that's a good question. Lots of students ask me that, and you don't need to worry too much. For example, what first degree you have. For example, our mechanical engineers often go into bioengineering, but the same is true for electrical engineers and even students who study aerospace engineering. Some of them go into biomedical engineering. So when it comes to your undergraduates, don't worry. I think it's good to do a first degree which you enjoy, but then there are lots of opportunities for specializing in a master's or a PhD in bioengineering. But even if you didn't do a specialist master's or PhD, it's quite common to go from straight mechanical engineering, joining a bioengineering company. So basically you need all-round skills, but then if you're really interested in that area, try to make your first company appointment into bioengineering.
The next one is how could AI become a bridge between nature's design and human engineering, helping us to solve problems that were previously impossible to understand?
Yeah, AI is a very exciting area, and it's enabling us to process information much faster, more efficiently. And there are some exciting opportunities in medical applications. It can take so long to go through lots of data. For example, if you've taken an MRI or an X-ray, and AI is very good at speeding up things. But we have to remember that you always need that human intelligence behind it, because whilst AI can be very fast and very efficient, it always needs that human ingenuity. One thing I could just add to what I've been talking about in this presentation, engineering is a very creative subject. That's why it's very fulfilling. And you need that human creativity behind AI. But AI is a very powerful tool that is helping us to understand biology and apply bio-inspired designs.
In your view, how important is it for engineers to learn from other fields outside engineering to become better, more well-rounded engineers?
Yeah, I like this. I like this question because one problem with modern education is that we've become very siloed, studying one subject. If you look at history, the pioneers of science were all-rounders, understanding all kinds of subjects. But I think in recent times, people are realizing that, yeah, you do need to be multidisciplinary, especially so for biologists. Many biologists are realizing that they have to collaborate with mathematicians and engineers, but the same true is for engineering as well. It's not just interesting, but it's really important to collaborate with biologists to understand how biology works. In my university, I teach automotive design, and with the help of musicians, I even had a lecture on beauty in music and how that it can inspire better car design. So I know from personal experience that it's really not just enjoyable but beneficial to collaborate with people in different disciplines.
Okay, before I move on to the next question, I would like to comment one, that your book design looked very much like Da Vinci.
Yeah,
Yeah, I like that.
yeah,
I like
it's a good comment. Thank you.
and another thing I wanted to say, I forgot. Never mind. Okay, next question by Mr. Bhutto, Sanghar Bhutto. Prof, is there any proper manufacturing methodology that is followed to make an artificial item inspired from nature or biology, like you showed about the prosthetic foot? Is this design driven by approximation at first to come up with the design or shape, or a proper manufacturing methodology for conversion from nature to man-made?
Yeah, that's that's a good question. Okay, the first thing I would say is when you're dealing with creativity, it's not easy to define a methodology because ultimately creativity is producing something that didn't exist. One of my favorite quotations is, scientists describe what is, engineers create what never existed. And it's easy to underestimate how difficult creativity is. But nevertheless, you still can produce methodologies. The second thing I would say is engineers want to be inspired by nature. They don't necessarily want to copy it exactly. One of the key skills you need if you're into bio-inspired design is to recognize which parts you really need to copy and which parts you don't. When we produced our robotic knee, we didn't put the ligaments in the middle of the joint because it created problems. So we thought we'll just put the ligaments at the outside. So we were trying to copy the things that gave us the best benefit, but not necessarily copying everything. So one important part of the methodology is to recognize what are the things that need to be copied, what are the things that don't need to be copied, what are the things that are practical to be copied, and what are the things that are just too difficult to copy. That's not easy, but that's definitely one of the key things you need to do. There is research going on at the moment about what are the detailed methodologies for following a bio-inspired design. process, but it'll be impossible to make it exact because it depends on the context, on the type of bioinspiration. But it's a really good question.
Okay. On a personal note, Prof, I notice a lot of your publications are on biomimetics and mechanical design journals. How much of these are actually read by proper medical professionals? Do
Yeah,
you get comments from them?
that's a really interesting question. Well, that actually gives me an idea because, for example, the review paper I did on linkage mechanisms, in the last 4 years, it's had 45 citations.
Yeah.
So what I need to do, I can look into that and work out what are biology papers and what are engineering papers. And I can, if I did that for all my papers, I could produce a bit of a study actually.
Yeah, yeah.
So I can get back to you with an answer to that. But actually, this whole area is still really an emerging area, and people are thinking we still need more collaboration. For example, I think in education, we're really behind the curve on teaching engineers biology and biologists learning engineering. For education, we're behind the curve. But even on research, we need more of it. But that kind of study to see citations would actually give us a concrete way of answering that question.
Yep. All right. Coming back to question by Dr. Nashrul, how can you see the future of biomechanical study and how this can be integrated with other biomedical engineering studies such as biomaterials, etc.?
Yeah, I think there's scope. In my travels around the world, I have noticed a little trend, universities wanting to expand, for example, MScs into bioengineering. They realize it's a growing field and there's a growing demand from students. So I would recommend every university to particularly look at this area for producing MScs in bio-inspired design. One of the challenges that we have is this. Engineering is already a very complex subject, very demanding. Biology is a very complex subject and very demanding. So when you're working in bioengineering, you need a very clever kind of person to run that degree course because they really have to be efficient in working out what we need to know. It's a great challenge. But these are some of the most important MScs. They're very attractive to students, but they have to be very well designed. So put some of your best academic staff on those programs.
That brings me to mind. That brings to mind, like back in Malaysia, what do you call hybrid degree does not seem to be quite popular, and teachers keep telling students, I'm not talking about university level, lower level, keep telling students keep to standard what do you call standard studies, electrical, mechanical, do not do all this bio and mixed hybrid kind of studies on a job scope level and all that. I may agree with that on a statistical basis, but when it comes to things like what you are doing, it seems like a hybrid study is quite necessary.
Yeah.
Okay, next question is back to our producer. Can an engineer fully understand complexity without engaging with philosophy, ethics, or theology? When engineers innovate, are we creating something truly new, or are we uncovering patterns that already exist in nature or the universe?
Okay, maybe if I do the second one first. What we're discovering with modern biomimetics is we're now finding that designs that we come up with are already there in nature. For example, those linkage mechanisms, it was a great surprise that engineers thought they had invented linkage mechanisms, but they were already there in fish jaws and human joints. a few years ago, there was even the discovery of gears in some hopping insects. So often we like to think of humans as being the inventor of everything, but it's already been invented there in the natural world. But it's still fun to innovate, and it's good to have that helping hand of looking at the natural world. The first question is kind of more profound. Can an engineer fully understand complexity without engaging philosophy, ethics, theology? The first thing I would say is that the great pioneering scientists like Isaac Newton, Boyle, James Clerk Maxwell, Lord Kelvin, they said they were really inspired to do their science because they believed that there was a creator who'd created all things, an intelligent designer. And I would agree with them. I would say I've been inspired by believing in intelligent design. To give a concrete example, when I was thinking of the knee joint and the foot, I was expecting to find sophisticated design because I thought this has surely been designed. And that encouraged me to look in detail at the design. Whereas I know other researchers who, because of Darwinian philosophy, it kind of teaches there should be examples of bad design in nature because evolution is restricted to step-by-step change. And those researchers have thought, well, I'm not going to look at the knee joint because it must be a bad design. So I feel that they've been held back, whereas I've been inspired to look more in detail. So I think that philosophy, ethics, and theology can have an impact on the efficiency, the effectiveness of a designer, and that's been my personal testimony.
So I think, Prof, but my question about is you cannot have this kind of thinking if you don't think about you don't love philosophy, you know, see the nature and everything. But because right now, I think that the new generation, they don't care about the philosophy, but it cares about how to live, you know, how to get money. So I think this is one of the missing in education right now, because people should, you know, when you see nature, you can think about this because you have some kind of philosophy, ethic, or theology behind this. You start to thinking, and then your curiosity develop. So I think this is very important in the education right now.
I think so. If I can add one more thing, one of my first books on design in nature was called Hallmarks of Design, and in that book, I also expressed my belief in intelligent design. And I actually had a letter, very surprisingly, from the then Prince Charles, now King Charles. And he wanted to say he supported my view about belief in intelligent design.
Yeah.
And he actually quoted from my book in one of his Wreath lectures, and it's actually on the web now. And he basically said he agreed with me that we should not ignore the work of a creator. But his argument was he believed that King Charles believed that people would have more care for the environment if they had a theological perspective. If we just ignore these things, then people are more likely to just neglect the environment and not care about the environment. And so so he agreed with me that we shouldn't just have a naturalistic view, ignoring all philosophy and theology. So I was very encouraged when Prince Charles supported me in that way. One of my colleagues joked that, well, I said to my colleague, he was very brave to say this in public, but my colleagues joked with me and he said, well, he's not brave because he cannot be sacked or demoted, or he cannot lose his position.
Actually, throughout your lecture, I was wondering who thought the creator of physics, chemistry, biology.
Yeah, exactly.
I mean, to embed the things, to grow the things, to make it such a way, and wow,
Yeah,
fantastic.
to me, it's the hallmarks, definitely the hallmarks of a designer. Yeah. It's superior to man-made
Yeah.
technology always.
Yeah.
Yeah.
All right, next one by Mohammad Shami. What challenges do bioengineers face when trying to mimic the complex motion of human fingers in robotic or prosthetic designs?
Yeah, this is an important question because engineers would love to create, robot hands. Many companies are very keen to produce a humanoid robot that can help in the home. Millions of dollars are going into investing in better robots. So this is very much a key question for today. Basically, it is incredibly difficult to make such a compact finger. We don't have the lubrication ability of synovial fluid. We don't have the ability to pack so many tendons into such a small space. Of course, biological systems are regenerating themselves all the time. So the joints in the fingers are always producing their own synovial fluid. There's self-healing, there's self-maintenance. We cannot replicate the sensors in the fingers, particularly the pressure sensors. We have thousands of touch sensors on the tips of our fingers, and engineers have tried to produce pressure sensors like the sensors in human fingers, but our pressure sensors are enormous compared to the pressure sensors in the fingers. We cannot produce wiring as small as the nerve pathway. So we're having trouble miniaturizing parts and components and miniaturizing the assembly. We're having trouble copying the complexity. We're having trouble copying the efficiency of human muscle, the power density of human muscle, the efficiency of human muscle. So, and also a key challenge is producing the connectivity. Ligaments are very efficient at joining bones together, and we cannot copy the material properties of ligaments and that efficiency of, so it's really every element of design we're struggling to match the human design. But each year that there is a bit of progress, but huge, it's a really exciting area of research, producing better robotic fingers.
Brother, your microphone, brother.
Oh, sorry. Before I go on to the next question, there's a offering from Mr. Azhar Hossain. Thank you so much for sharing, Prof. My mother is suffering from knee ache for some time now, and I'm offering her as a guinea pig. Perhaps putting the knee prosthetic would be the best cure for her.
Yeah, now is a good time for knee prosthetics because they have been really fine-tuned over the last few years. So they're becoming very reliable operation, and they can last quite a long time. The only drawback is you get less range of motion, but for many people that's not too big a deal. So now is a good time for that.
Okay, all right. Something more serious by Deputy Producer. Looking back at your career, what advice would you give to young researchers who want to work on high-impact engineering projects?
Yeah, I think decide on what area you'd like to work on. The environment, you can make a big impact on research into better green but project areas. Decide if you want to be in bioengineering, decide if you want to be in robotics or aerospace. So be clear which sphere you want to work in, because each sphere is so complex. It's normally you can only make a big impact in one area. So choose that area, and there are lots of areas where the world needs engineering solutions. Then try and work in the best research center or the best company. Some companies have a vision, a very creative vision of making a big impact. Other companies maybe just want to make money, just want to make components. So choosing the right company to work for is a very big decision as well. So make those big choices correctly early in your career.
Okay, Prof, on that note, I just noticed that your basic degree says BSc bracket engineering. How is that?
Yeah, my first degree was in London at Brunel University, and in those days it was very common to have a Bachelor of Science. Now it's very common to have a Master of Science in Engineering, but in my day you could learn engineering in 3 years. This was going back over 40 years.
Yeah.
I went straight from a BSc to a PhD, but today it's almost always and very highly recommended to do an MSc before you do a PhD.
Yeah. All right. Thank you. Okay. Greetings, Prof. Stuart. I'm Mark Woon from Sarawak, East Malaysia. Thank you for, Borneo. Thank you for your lectures and sharing valuable experiences. I'm inspired, especially on the mechanisms. This leads to inspiration for a range of stiffness in a design in whale flippers or bird wings. Would be grateful if you could elaborate more on your experience. Thank you.
Yeah, thank you. Obviously, I didn't have much time to go into the vertebrate limb pattern. That paper, by the way, is open access and free to view. Many papers are not free, but that one is. So I'd encourage you to look on the Journal of Bioinspiration for more details. I have 50 diagrams in that paper. The reason that particular paper was important is that robotics engineers need to know, is the vertebrate limb optimal or not? Should we be copying it or not? And Darwin, because of what he said, was leading many robotics engineers not to copy, but my paper helped explain to robotics engineers, yes, you should be copying because the vertebrate limb is always optimal. One of my favorite examples of that was with frog legs. They have a remarkable leg design for making enormous leaps. The joint between their lower back and their leg even has an extra joint so they can align themselves, and which has kind of lessons for rocket design. So the vertebrate limb, it's a really fascinating area in every single animal, whether it's a frog or a cat. You see it fine-tuned for that animal, and that's going to be really helpful in robotics design. So I would encourage you to look at that open access paper.
Okay. Last two questions. Hi, Prof. What do you think about the exploratory research versus applied research in engineering? It's always a gray area when to do research in university that offer engineering programs.
Yeah.
Exploratory versus applied.
Yeah. I mean, engineers, I think all scientists like to do kind of exploratory research, but of course the challenge is then getting funding for that, because funding is now very, very competitive. In some ways, this is a question for the funding councils. I would recommend funding organizations to allocate some funding for purely exploratory research. I mean, it's more common in physics where you can look at fundamental particles or looking at the universe. But in engineering, I think we could do with some of that exploratory research funding where we could just look at biological systems in general to look for lessons without worrying about making a profit. One of the grants I had was from the Royal Academy of Engineering, where I was allowed to do exploratory research. I found that really effective. So hopefully funding councils will do that more in the future.
So what you're saying is just go ahead your early years, in your early years, building up your portfolio.
Yes. Yeah, definitely. Yes. Yeah.
Okay, one question here. Good, the last one. Good morning, Professor. In terms of natural lubrication that you have studied, is there any chance that throughout chemical engineering, the properties of the lubricating fluids can be replicated?
Yeah, that's what engineers and chemists are trying. If you look up papers on hydrogels, you'll see lots of papers where they're making progress. The challenge is it's not just the lubricant. In order to copy natural systems, you need to copy the cartilage as well, which is a porous, flexible material. So you're not just copying fluid, you're copying the whole system. In natural systems, they also regenerate in that case, the proteins, the lubricants. So it's like a living system. So it's not just a lubricant, it's the whole system. And if you look up lots of papers on hydrogels, you'll get some insight into that.
Okay, I think that's about it. And one last question from me, Prof. What I wanted to ask was on your involvement with ESA, European Space Agency. Was that related to your biomimetics or was it something different?
Actually, there is a connection because what I designed with ESA was a robotic arm. I mainly worked on space robotics.
Okay.
And one of the main arms I had was a triple hinged arm with a shoulder joint, an elbow joint, and a wrist joint. And so I was kind of inspired by the vertebrate limb in my robotics. So there's often more of a connection than people think if you work in different disciplines.
Okay. All right. That's for the morning. Thank you, Prof, for that wonderful re-engineering, especially mine. I don't know about the rest, but I had a complete redirection of what mechanical engineering is all about. Okay. And before we bid you farewell, we'd like to have a group photo with you. So everyone, as is usual, please switch on your cameras. Cameras, guys, cameras. Mr. Bhutto, are you from Pakistan?
Yes, I'm from Pakistan, but currently doing PhD in UniMass, Sarawak.
Okay, all right,
PhD.
UniMass. All
Yeah.
right.
My topic is also bioinspiration, coastal protective structure.
Okay, thank you for joining us.
Yeah, inspired from mollusk shells. It's
Mollusk shells.
structural geometry, macrostructural geometry, and converting that into the macrostructural concrete.
Okay.
Or block.
Nice. Okay, cameras are on. Ahmad Shakirin, your camera is off. Azarul, Dr. Nash, Zokan.
So probably we have a video of this.
Oh, video.
We have a video to officially changing the name of ISICS to the
The second page, all the guys' cameras are all off. Third page, cameras are all off. Only the first page camera is on. Shah, whenever you're ready, camera. Okay.
Okay, I think we just wait for the last video.
Okay. All right. Before we shut off for the year, we'd like to announce that the name ISICS would no more be used starting next year. We are rebranding our ISICS International STEM series into Cosmos of Curiosity. So to more balance out the range of speakers and the range of topics that are planned from now on.
So Shah, can you play the video?
Oi.
What happened? Hope it's okay. So I think we have some kind of internet problem. So yeah.